So we'll get going on the third and last session of the day. John Mason probably doesn't need much introduction from me. Most of you will know him from various places, but John is the director of our BAA Meteor section. He also is a key person in the South Downs Planetarium down in Chichester. So if you ever happen to be down in Chichester, go along to the planetarium. It's a great show they have there. It's rather different to the show that we saw earlier this morning, which was a big digital projector. The South Downs Planetarium has the old Zeiss projector, I believe, from Armagh Planetarium.
Yeah, from Armagh.
So John's going to talk to us about the connection between comets and meteors. And it's very important that I point out that John also has a Blue Peter badge. And an MBE as well, which is...
The Blue Peter badge is far more important.
So, John, over to you.
Thank you very much, Nick. It's a great pleasure to be here today to talk about the link between comets and meteoroid streams. These days, with modern video camera networks, it's very easy in a fairly short period of time to collect a large amount of data on meteor orbits and the radiance of those meteors. And this plot from nematode data, 12 years of nematode data, 20,500 radiance points of the major annual meteor showers. Now, we can see one or two well-known, like the Perseids here, for example, the Geminids here, the North and South Taurids. And over the years, we have these meteor showers, some major, some minor. And the interesting thing that we want to try and determine is, what is the origin of these meteoroid streams? What is the progenitors of each of these streams? Now, in the main, they are periodic comets, although there are some streams that appear to be related to bodies that may be defunct comets that look a bit more like asteroids, but you know, maybe a dead comet does look a bit like an asteroid, we're not too sure. So the thing we're trying to do then is to look at the orbits of these individual meteoroids and match them to that of comets we know, or even of comets and objects that we don't know. Now, the dust that's being produced that gets into these meteoroid streams comes in the main from periodic comets. When comets are approaching perihelion, and as we've seen from some time afterwards, they release an enormous amount of dust. That dust is dragged out from the icy nucleus by the escaping gas. So inside, you've got the ice with a dark, dusty crust on the outside, and where the dusty crust cracks, you get these fissures where you get these fountains of gas dragging out dust grains. And those dust grains can range from micron size up to millimeter size grains. Now, those grains will be ejected from the nucleus with a certain velocity, and they will, over time, develop velocities which are similar to, but very slightly different to that of the parent comet. And as a result, that dust will slowly disperse from the nucleus, moving behind the nucleus in the comet's orbit and ahead of the nucleus in the comet's orbit. And this lovely image that we've already seen earlier of 2006 P1 McNaught shows the incredible amount of dust that can be produced by a cometary nucleus. Comets typically produce between 250 kilograms and several tens of tons of dust per second. And a short period comet, a duplicate comet, might release something between 1 million and 100 million tons of dust each orbit round the sun. Now, we know that there are some very active longer period comets that have far higher dust production rates than that. But that is an enormous amount of dust being ejected into the interplanetary environment by these comets as they move around the sun. So here we've got the orbit of our hypothetical comet. It might be prograde, might be retrograde, and there we've got the orbit of the Earth. Now, there will be many, many comets producing meteoroid swarms, and we never see members of that swarm because the stream does not come close enough to the Earth's orbit. What has to happen is that one or more of the nodes of the comet's orbit needs to be within about 0.1 astronomical unit, in other words, about 15 million kilometers of the Earth's orbit, for us to see the dust from that stream. There will be a great many comets that have produced meteoroid streams that we haven't seen and we will never see, because that dust never comes close enough to the orbit. But there are a lot of comets where the node of the orbit comes within that 0.1 AU of the Earth's orbit, and then we will see particles from the stream. In addition, because of planetary perturbations, cometary orbits are always evolving. And so it may be that you don't see the members of a stream for some time, and then the orbit evolves and it comes close, and we then start to see members of that particular meteoroid swarm. Here you see a high inclination orbit, and we can see that one of the nodes of the comet's orbit comes within the required distance of the Earth's orbit, whereas the other one is some way inside. In most cases where a cometary orbit approaches within 0.1 AU of the Earth's orbit at the node, we will only see it at either the ascending or the descending node. There are exceptions. One of those exceptions is the meteoroid complex associated with comet Encke, and the other one with comet Halley. So the first two periodic comets to be identified, 1P Halley and 2P Encke. In both cases, we see material from that stream at both the ascending and descending nodes. Now, we can divide the comets that we see into a number of classes, and so far today, they've generally only been divided into two groups. I'm going to divide them into 5. And these are the first two groups of comets that I'm going to talk about. The long period comets, comets with periods over 200, 250 years that arrived fairly recently from the Oort cloud. They have direct and retrograde orbits, and they are particularly interesting. And then the Halley family comets. Most of the meteoroid streams that we're familiar with generally come from the Halley family comets. So let's have a look at some examples of those. So of the long period comets, there aren't that many of the major meteoroid streams that are in fact linked with long period comets. Some of these minor streams are linked, but the one that's best known is the one with 1861 G1 Thatcher, and that is the April Lyrids that come up in about the 3rd week of April every year. That's probably the best known of the meteor showers associated with long period comets. Now, those are the most well known. In recent years, there have been a number of attempts to link other minor showers with other long period comets. Perhaps one of the best known is the one that's connected with 1907 G1 Grigg-Mellish, and that produces the Delta Pavonid meteor shower, a southern hemisphere shower. We don't see that from Britain, and that had an outburst in 2019. But there are a number of others, and this is work in progress, people trying to look at orbits of meteors that are being detected and link them with the orbits of long period comets. But probably the meteor showers that are best known are the ones linked with the Halley family comets. Now, comet 1P Halley itself, we see both at the ascending and descending nodes, meteoroids from the stream, the Etoacarids at the beginning of May and the Orionids in the 3rd week of October. But of course, coming up very soon, we have one of the most well-known of all the Halley family comet streams, 109P Swift-Tuttle, the Perseids, which peak in the just before the middle of August, and this year coincide with a very dark skies. There is no bright moon about, so hopefully we'll have good conditions for the Perseids this year. And then we have the Leonids, associated with Temple Tuttle, which also, of course, have produced some of the greatest meteor showers and storms of the last couple of 100 years. So let's just look at 3 examples of those Halley streams. The Perseids, of course, this is a typical rates curve for the Perseids with a fairly sharp maximum peaking about solar long 140. And that's a shower, of course, which has been very well observed over many, many years. The history of the shower goes back nearly 2,000 years. But the Perseids, don't imagine that because you get used to this sort of curve, that the shower always produces the same activity. It does not, which is why it is invaluable to keep observing these major showers year after year, because in 2016, there was an unexpected outburst in addition to the normal maximum. How could this happen? Well, this is because the idea that we used to have of the way the dust in these streams was distributed was wrong. The old idea, if we go back 25 years, the old idea was that the dust was distributed in a sort of a long sausage extending around the comet's orbit. And the dust was denser in the middle and less dense towards the edge. And as the Earth ploughed through this cylindrical sausage-shaped region, you got dust, the number of dust particles increased towards the middle, and then as you went out the other side, it went down again. And the sort of graph that I showed you just now was fairly typical for that. But it's not like that. Every time a comet goes round the sun, it lays down a filament of dust from that particular orbit. And when it comes round another time, it'll lay down another filament of dust, the orbital elements of which will be slightly different from the orbital elements of the previous filament. And when a comet goes round many, many times, you get lots and lots of these filaments. So I want you to imagine now a large fat sausage. We're looking at the cross section, and we're going to thread these bits of spaghetti through it. So we're going to thread strings of spaghetti through our fat sausage, and as the Earth goes through, it might miss those bits of spaghetti, then it might hit a couple there, and then it might come out the other side. So there's 2 components. There's the broad background, which is the dust distribution within the sausage, and there are the intense elements of the shower contained within the spaghetti-like threads, filaments, dust trails. And this is an aspect of meteor showers that we never really realized until about 25 years ago. And it's now completely captivated our thinking about meteor shower activity. And so this is due to one of those filaments. The main period of the shower that we see rising and falling is going through the sausage. But here we happen to hit a strand of spaghetti where the dust was more densely packed and hence rates twice as much. So the reason it's invaluable to observe these showers is to detect the location of these filaments within the main shower, because this tells us a lot about the evolution of the comet and the meteoroids from that comet. The Orionids connected with Halley's comet, they generally produce fairly consistent rates of 20-25 an hour at peak. But in 2011, there was a major outburst in the Orionid shower for one night, and you can see a beautiful view here from Phil Hart showing all the Orionids at that time. Again, the Orionids, very old shower, obviously lots and lots of meteors seen over a long period of time, but occasionally you get one of those filaments of enhanced activity. But the Leonids, of course, are somewhat different. In the case of the Leonids, even though the parent comet has a period of about 33¼ years, the dust does not appear to be evenly spread around the orbit. There is some dust all around the orbit, giving low rates throughout the 33 years, but it appears that the spaghetti-like threads are only found a few years ahead of and behind the parent comet's perihelion passage. So that's a rather different distribution of dust, and we don't fully understand why it is that the distribution of dust in the stream from 55P Tempel-Tuttle is different from many of the other comets of similar period. There must be some aspect of the nucleus or the way the dust is being emitted from that nucleus, which means that we do not get high rates at intervals when the comet is at any point in its orbit, only for 5 years or so before and after a perihelion passage. So that's a rather different case. 3 other classes of comets that produce meteoroid stream. Jupiter family comets. These comets may have originated in the Edgeworth-Kuiper belt and then were perturbed inwards. They are generally short period, with periods of 5 to 7 years with direct prograde orbits. Encke family comets, which have even shorter periods. Obviously, comet 2P Encke is the prime one there, and we'll talk about that in just a moment. And then a bit of an oddball here, and this is 2003 EH1, which may be a fragment of the comet 1490Y1, and that is almost certainly connected with the quadrantid meteor shower that we see at the beginning of January every year. So here is just a list of Jupiter family comets that give rise to meteor showers. And generally, these showers are not major. Occasionally, you get a burst of activity from one or other of these, but probably the most well-known is 21P Giacobini Zinner, and that has produced some really great meteor showers in the last century. So this is the main Giacobinid meteor storm of 1933. You can see that the meteor rates go up to nearly 100 meteors per minute at peak, but notice the peak is incredibly short. There was another meteor storm in 1946. This was the first one to be observed by radio and photographic means. And again, you can see this very short, abrupt peak of only a few hours. And again, visual rates were approaching 5,000 meteors per hour, but only for a very short period. So the Draconid meteors associated with Giacobini Zinner are perhaps one of the more spectacular examples of meteor showers coming from Jupiter family comets. Here you've got the circumstances of the 1933 and 1946 storms. Now, these are the dates of the filaments of dust that are in the Earth's orbit. So this is the Earth's tracking along in its orbit, and you can see it's going through here, a filament of dust released by the comet between 1880 and 1894. Then it goes to another filament released between 1900 and 1907. Now with supercomputers, we can put test particles into the comet's orbit, and we can watch how they evolve over time. And Jérémy Vaubayon has done a lot of work on this and identifying which particular dust trails are responsible for the major showers and storms that we see. In other words, which particular strands of spaghetti are giving us these outbursts when we see them. So over here, the 1946 storm, you can see, again, is due to dust between the 1900-1907 filament and 1933-1940. So this is very important in looking at when the dust was released from the comet, where it is in space when the Earth plows through it. Now, the Taurid complex is one of the most massive streams of material in the inner solar system. There are 4 showers connected with the Taurid complex, 2 at the ascending node, 2 at the descending node. It's a very, very broad stream of dust. But there are 2 other short period comets, 107P Wilson-Harrington, and this one, 3200 Phaethon, which looks like an asteroid. It might be a rock comet, it might be a dead comet nucleus, but that produces the Geminids, which is now the most active meteor shower of the year. And that has a very short orbital period. And then we have here, this is a Spitzer Space Telescope image of Comet Encke, and this is the comet, and this red diagonal line is all the dust, and Spitzer, because it saw in the infrared, picked up the dust very clearly. That is the dust spread around the orbit of Comet Encke, which, because its period is only 3.3 years, obviously has spread a lot of dust, which is distributed all over the inner solar system. And this is a lovely Taurid fireball. You do get some beautiful bright meteors from the Taurids occasionally. Generally, the rates are not very high in early November when the shower peaks. The Quadrantids, as I said, they are connected with a rather unusual body. We're not too sure exactly, but it's an object which probably doesn't exist anymore. It may be connected with that object 1490Y1 and a fragment of that. And the stream is evolving due to perturbations by Jupiter. It's particularly important to realize that Jupiter has a very big effect on many meteoroid swarms and affects their orbits, changing the orbit over time. And so when you're looking at when dust was released 200, 300 years ago and where that filament was, you have to take planetary perturbations into account to get it right for exactly what's happened to it since that time. And there's a typical peak from the Quadrantids. A very, very narrow peak, only lasts about a day, and then it's over. And unfortunately, you regularly get a lot of cloud in early January, January 3rd, 4th, when the shower peaks. But I want to finish with two very different meteoroid streams due to the destruction of periodic comets. Now, these images are of 73P Schwarzmann-Volkmann 3. We heard about another of the Schwarzmann-Volkmann comets earlier on today, but this one broke up in 1995, and by 2006, when these images were created, there were already over 30 fragments, and we now believe there are probably 70 fragments of this comet. Why are we interested? Because, and this is again is another Spitzer image from 2006, you can see the comets, the fragments that the comet has broken into are all these bright blobs all along here. But notice this strand going along. That is dust strewn all the way along the orbit of the comet. Now, it was known that this particular comet could produce a meteoroid stream that was visible from Earth. In 1930, the Tau Hercules shower was identified and associated with the comet, but it had never produced particularly high rates until the 31st of May last year, when there was an outburst of Tau Hercules associated with dust from the breakup, the 1995 breakup of 73P. So this is an example of a breakup shedding a huge amount of dust onto the orbit and producing an enhanced burst. But that dust is not spread all around the orbit, and the Earth does not intersect the filaments from that breakup every year. So it seems that the next time we'll get a major outburst from this is 2033. Oh dear, you say. Never mind, I'm coming up with something to cheer you up. Because here is another comet that broke up and was destroyed back in the 19th century. Comet 3, it was originally 3P Beaver, the third comet to have its orbit determined. And like the first two, 1P Halley and 2P Encke, it too is named not after the discoverer, but the man who worked out its orbit. Captain Wilhelm Biela, an army officer who was interested in comets, saw the comet in 1826 and worked out that it was the same of comets seen previously. It was actually discovered by Montaigne in 1772. Now, when the comet returned, and it had a period of 6.6 years, when it returned in 1846, it had been seen to have broken into two fragments, A and B. They came back in 1852, two fragments slightly further apart. 1859, there was no chance of seeing them because it was a very poorly placed apparition, and it was never seen again. Fragments of Comet Biela have never been seen since 1852, but in 1872, November 27, and again in 1885, there were spectacular meteor storms associated with the breakup of Comet Biela. And the dust ejected in 1846 and 1852 produced these two great storms, 1872 and 1885. We think that the comet actually broke up in late 1842, early 1843. These are the two peaks for the two years. And what we're interested in then is which particular dust filaments caused these enormous meteor displays. Well, again, you can see here some work by Peter Jenniskens and his colleagues, and you can see the 1839-1846 filament, 1839, 1846, 1852. So this is the period around the time of the breakup. 46 and 52 is the time the comet had already broken up. 1839 was the last apparition before the breakup. All of that dust came from that breakup. We are not going to see dust from those filaments for a long time. And we didn't think until 2011 that we were going to see them again. But in 2011, there was an unexpected shower, about 100 meteors per hour, from Comet Biela's debris. And this is a plot, and you can see that most of the dust is coming from the 1659 filament. No one had ever thought to go back before the comet broke up to see where those filaments would be. We only knew about the strings of spaghetti from 1839 onwards till it broke up. We didn't think of looking for where were filaments from earlier apparitions, and the 1649 was one that was key. And the good news is it's coming back this year. The 1649 filament will be intersected by the Earth in the first few days of December this year, with rates of possibly up to 200 meters per hour for a short period. We know very little about what's going to happen. It is absolutely essential that we get as many observations as possible of that shower, because this will be the biggest shower of meteors from this defunct comet since 1872. That is something that we should all be interested in. So I would urge you all to, if you've got cameras, you may need to make some slight adjustments, because these meteors are going to be slow but faint. And we also want to get visual observers out there as well. The maximum is not going to be that well known. We think it will be sometime, possibly 2nd, 3rd, 4th, 5th of December. We can't be sure. Let's hope for clear weather. Thank you very much.
Brilliant, John. Thank you very much. Although the mental image of a sausage threaded through with spaghetti is going to stick with me for some time.
That was the idea.
So, we'll make sure that the BAA News website have got more details about this closer to the time. So we've got time for a couple of questions for John. So any questions?